Without further ado, we'll introduce our moderator for today, Eloisa Acha. Eloisa is the Director for Research Relations at the Cockrell School of Engineering at UT Austin. Take it away, Eloisa.
Good morning, everyone, and hello. Welcome to our first text talk for the year 2021. Today, we will be talking about bioinspired membranes for sustainable separations. If this is the first time you join us, the format is the following. First, Dr. Kumar will share a presentation on the topic. As he presents, feel free to type in your questions in the chat box. During the last 20 to 25 minutes, I will moderate the Q&A section, and then we'll wrap up at the end of the hour. I'm very excited to introduce Dr. Manish Kumar. Manish Kumar is an associate professor of environmental engineering at UT Austin. He received his bachelor's from the National Institute of Technology in Trichy, India in chemical engineering. He completed master's in environmental engineering at the University of Illinois and then worked for approximately 7 years in the environmental consulting industry, doing applied research projects primarily centered around membranes for water treatment, desalination, and reclamation. He returned to Illinois to complete a PhD in the area of biomimetic membranes, and then conducted postdoctoral research at the Harvard Medical School on the structure of water channel proteins, aquaporins. He works in the area of sustainable filtration, biophysical transport characterization, protein-based membranes and devices, and on developing artificial membrane proteins. His group also works on improving membrane processes to prevent biofouling and colloidal fouling, and for treating water for unconventional oil and gas operations. At UT, his new initiative is on creating bio-inspired synthetic membranes for gas and hydrocarbon separations and other industrial applications. Welcome, Manish, and I hand over the microphone to you.
All right, I'll turn on my microphone before I say something. So people can see my slides, I hope. I think you can. All right, so thank you, Eloisa, for introducing me. My name is Manish Kumar. I am somewhat new to Austin, and I'm very excited to give this presentation. I took a look at the list of people coming to this talk, and I saw quite a few familiar names. And I wish I could see you all. I wish I could meet you all, but it'll happen soon, I think. So my talk today will have one theme that you'll see come together. But before I go to that, let me give you introduction and pictures about my research journey. And this is unusual, but it's taught me a lot, and that's what I want to take you through today as well. So I came to the US in 1998 to do some research work and get an MS. I ended up completing the MS and working in industry primarily on membranes for water purification. It was a great time. I spent time in Phoenix, Arizona, and then in Southern California. And this was the time that membranes was really entering the wastewater treatment market, and it was a great time to be in the field. But I always wanted to be a professor, so I went back to Illinois to get a PhD. And this was in this area of biomimetic membranes. I didn't know much about it, but I was very fascinated. I wanted to do something interesting. So we showed during my PhD that you could put proteins that transport water in our bodies, they're called aquaporins, into polymers, and they still work. So that was very exciting for me during my PhD. Got really intrigued by this, and I did a postdoc where we used cryo-electron microscopy to solve the structure of the eye lens aquaporins. So these were eye lenses from sheep. Similar proteins exist in our eyes, and we used cryo-electron microscopy, which is a pretty big deal now, to solve the structure of these proteins. And then I moved to Penn State, and there my focus was both these kind of proteins to make membranes, and then we started working on artificial constructs, something that's made using organic chemistry to copy the structure of these proteins so that we can actually make membranes using artificial water channels. So at UT, what I'm trying to do is to take all this learning and see if we can make things that can go in this direction to this scale. So that's what we're going to talk about. But the whole talk is about separations. And separations are huge, is what I say. So one note, whenever you see a grayed out reference, I've made it available. And I think you'll see it in the chat, a link to these presentations. Sometimes they are from my own collection and sometimes they're freely available. So those of you that don't have access to these papers, you can probably download them now. But this paper over here showed us that separations are very important for energy sustainability. So here's a figure, and let's walk through this. The first few lines were mind-blowing for me when I read it. Chemical separations account for about half of US industrial energy use. So, and 10 to 15% of nation's total energy consumption. So it's a pretty big deal. And then the other big thing to see is if we don't use thermal separations. So thermal separations are where you change phase from a liquid to a gas or a gas to a liquid to try to do some separations, and that costs a lot of energy. If we could replace that by using membranes where there's no phase change, you can save 90% of energy. So this is what frames what we do around membranes. And membranes have become a really big deal for many different industrial applications, as many of you know. And these include applications in water purification. This is a desalination plant where you remove salt from water. Gas separations for carbon capture type applications, or just air purification, getting oxygen and nitrogen from air. Bioseparations such as what's done now to make vaccines. The Moderna mRNA purification process has many ultrafiltration, diafiltration steps that could be beneficial if you had better membranes. And then food and beverage applications such as making lactose-free milk. So one of the major things that you immediately learn when you start working with membranes is all membranes, all current membranes have this thing called the permeability-selectivity trade-off. So let's walk through that. So if you're separating oxygen from nitrogen, this x-axis is the permeability of oxygen. So you want a lot of oxygen coming through your membrane, but then you don't want nitrogen coming through the membrane. So your selectivity has to be high too. And this trade-off line shows that as you increase the permeability or the production rate of oxygen, your selectivity will go down and you'll start getting nitrogen in your product. So that's a trade-off curve, they call it. Same thing with reverse osmosis used for desalination. You want water, you don't want salt. But if you produce a lot of water, then your selectivity is low. So you'll have salt coming through in your permeate or your product. So usually for desalination, you want it to be about 10,000. So you have 10,000 water molecules going through, and then you have 1 sodium chloride going through. So something like that is what you need to think about in selectivity. Same thing for proteins. If you're purifying a monoclonal antibody, if you have very high permeability, then you'll have a very low separation factor. So this challenge has been there for polymeric membranes for a very long time. And to understand this, let's talk about membranes a little bit and their types. And this is a very simple figure, and it's not all kinds of, this is for gas separation membranes, but it applies to all membranes. So you either have holes or you don't have holes. And if you have holes, if you have molecules bigger than the holes, they'll go through. If they're not, they won't go through. Now, dense membranes are something special. Here, there are no holes that go all the way through, no pores that go all the way through. Your solute that you want to separate actually has to dissolve into the matrix of the membrane and get through, and then diffuse in the matrix and then come out. So if you have 2 molecules, they have to have diffusion, different solubilities and diffusivities through the membrane. Now, there's one more view I want to show to you. So this is what we talked about now. This is a classic membrane book. If you look at the molecular level, you have all these polymer chains wrapped up, and then you have some free volume in there, some cavities in there that we call free volume. And if you have a molecule here, for it to get to this part, what happens is these chains actually move because of thermal motion, just because of, say, room temperature. And then once in a while, this will jump through to this side. And through these jumps is how solutes move inside a solution diffusion membrane. So very, very unintuitive, but this is well known for us. So now if you think about selectivity, we're talking about permeability and selectivity. So if you have a porous membrane, it's quite easy to understand. If you have pores of all the same size, you have very, very good selectivity. So rejection is how much you reject and how much you pass through. So if you think about a pore and it has the same size, if you have a solute that has the same size as the pore, mean size of the pore, anything bigger than the pore should just be rejected, right? But if you have a distribution of pores, and this shows you the variance in the distribution and the mean size of the pore, if you have more and more variance in the pore, if you have pores of different sizes, that even if you have the right size pore, things will sneak through, right? So this is the problem for porous membranes. And this is well known, and you can really imagine this, right? You have a big hole, you have a solute coming down, it'll just go find the big hole and go through. So you lose selectivity. So this is well known. Again, this is grayed out, so you can actually read these. But this picture is not very clear for non-porous membranes. So I'm going to take a little bit of a detour and tell you about this recent study we did that somehow clarifies this and gives you a better picture for non-porous membranes, and specifically for my favorite type of membranes, thin-film composite reverse osmosis membranes. So whether you know it or not, it's present everywhere. So thin film composite reverse osmosis membranes are used for seawater desalination, brackish water desalination, wastewater reuse if you're recycling wastewater. It's also present under your sink if you use reverse osmosis at home. So it's a very, very widespread technology that's everywhere, and every membrane looks like this. And it's a very thin selective layer, so the layer that does all the separations is only 100 to 300 nanometer thick. It's on a porous support, which is made of another polymer, but it has bigger holes. And then there's a fabric at the bottom. And it's this chemistry called interfacial polymerization, and I'll tell you more about that. But these kind of membranes treat at least 60 billion gallons of water per year. And if you convert that into how much area, it's 2 million square meters per year. So if you talk about scalability, this is the champ in polymer materials used for applications. And it's a very rapid roll-to-roll process. It's a very simple process in one sense. It has challenges, and we'll talk about this later, but for some applications, it's hard to control defects in here. But industry, all these people have got this down. They can make membranes that can do desalination, no problem, all day. But the challenge is we really don't know how it works. So what my colleagues do in the field, and we worked with DuPont. DuPont's not here. It used to be made by Dow Water, now it's DuPont. My colleagues at DuPont that we collaborated with, they can come up with very different chemistry, different types of chemical tricks that give them very good performance, but they don't know how to connect this chemistry to the performance. It just works. So what I'm going to show you is where we tried to make this connection between structure and performance by thinking about what the polymer actually looks like at the nanoscale. So that's what we're going to talk about a little bit here. So if you think about interfacial polymerization, these are non-porous and non-homogeneous, which we're going to get to. But what you do is you take a porous membrane, and on top you add this monomer. This is the diamine, so 2 amines here, in an aqueous solution on the surface. And then you put this TMC, which has this mesoyl chloride groups, in an organic solvent, like hexane, for example. And then at the interface where these two things mix, or don't mix because they are immiscible liquids, right? That you form a membrane that looks like this on the right side. So it looks quite crumpled and complex. And you even see some, looks like you see some voids in here. So this is a 2D picture we've had for 30, 40 years of these membranes. And there's been lots of speculation about where the holes are and is there voids in the membrane or not. So the problem is because we have 2D structure information. So we have slices here, or you can take a picture from the top using an electron microscope. It really looks like nothing. You sometimes feel like there are holes here or there are nodules here. So this is a problem because you really can't understand what's going on in there by these pictures. So it's almost like you have a box full of things and you slice it, and sometimes you see something here, and sometimes you see something here. You see different things at different slices. So it's like in CAT scan, right? So if you just see a static image, it's very hard to see, but if you tilt and take pictures from different angles, you can get a 3D reconstruction. So this is what we wanted to do. And we took this commercial membrane from DuPont, who were our collaborators on this project. This is a regular commercial seawater membrane in this case. And here's a picture when you just take one picture, right, just off the top. And then you tilt it -65, and you take hundreds of images on one side and hundreds of images on the other side at different angles. And then what you could do, you could put it together. And again, this will mean something, but not much right now. So what you see is you're going through the depth of the membrane. So you can see where there's space and then there's no space. And then finally, you can reconstruct a 3D volume from this. And this 3D volume shows you all the roughness in the membrane. But again, does that really tell you anything? So it does. What it does now is this. So if you go back here and go to the end here, finally, you have this. But the technique we used a dark field, a high angle annular dark field stem technique. So where you take you raster an electron beam across the membrane, and you make this image where each voxel, the intensity of each voxel, which is the equivalent 3D equivalent of a pixel, has mass information. So intensity of the voxel is equivalent to mass, and you know the volume of the voxel. So you know density, and that's a huge deal. So now at the nanoscale, you have density. And what does that do for you? So you see on the left side, we can get a density distribution throughout the membrane. And when I play this over here, you'll see that we are slicing through a membrane in the y direction about a few hundred nanometers or up to a micron in the flat direction. And you can see all the red stuff showing up, right? All these red and yellow are high density areas. And if you look closely, it looks like they are really on the top of the membrane, on this very tough, dense membrane or very rough membrane. You have it right at the top, the highest density. And it's broadly distributed. And through some other tricks that's in the paper right here that you can download right now, you can actually see that you can convert this density into something called free volume. So remember the picture of the polymer I showed you with a particle in there or a molecule in there, the space that's occupied by a polymer versus free volume. So the free volume, the fraction of the free volume that this occupies. So this is important because if you can get this value, you can get diffusivity. You can find out how fast water is moving around in there. So this was all good, but all this is a distribution. All you want to know is how does water go through it? And this was never been done before. And even this level of detail on the density was not present. Now we can answer some questions. So what we did is we took 4 membranes that DuPont made, and I'm going to show you 2. So this is a reconstruction of one. This is a reconstruction of another. This PA4, they did some tests in the lab, and they found that it's a thicker membrane, but it has much more water permeability and the same salt rejection as this one. So they were mystified because if you have something thicker, it has more resistance, less water should go through. So this was a good test case for us to test out our ideas. So what we did is we did whatever I showed you earlier, so we can get density. But what do you see on the right side? You see that the density is really sharp and really contained in a very small distribution, while this is very broad. The other thing you see is when you make the conversion to fractional free volume, you also have very sharp values. And if you look at diffusion coefficients, they are high, about the high end of this, and they are in a very, very narrow value. So this gives us a hint, right? It gives us a hint that when you have lots of density distributions and high densities, your water molecules, so this is a simulation that our colleagues from Iowa State did, and they showed that if you have very high density, so only the very high density areas are shown in this membrane. This is the upstream side of the membrane, and the bottom is the bottom side of the membrane or downstream side of the membrane. You can see that these water molecules have to go and bend and twist to get through when you have distribution of densities that are all over the place. So this is what causes problems, I think. And this is what we show here. So so the title says, can predict permeability without even testing in a pressure cell. I'll talk about that in a second. So these are the 4 membranes we tested. And we did the simulation I just showed you by connecting all the different diffusivities or the densities together to make a 3D picture. And then we simulated water transport through. And you can see here, the top layer has a flux distribution or water flow per unit area per unit time distribution that's very wide, right? It goes from all the way 40 something, all the way down to almost 0, these blue areas at the top and at the bottom. While this one, which is very high permeability, has everything in this range, 40 to 30 range. So it is much more uniform because the density was uniform, the free volume was uniform, the diffusion coefficient was uniform. So this leads to this being very high permeability. And then if you look at that trade-off curve, remember I was telling you about the 10,000 number for desalination. This is about 10,000. And this PA1 is a commercial type membrane, which has a decent selectivity and high permeability. This PA4 has the same selectivity, but 30 to 40% higher permeability. And we can now explain why. So this is the design principle we've been looking for a while. So all this is good. We can make better membranes. But more important is that we develop tools that can understand the effect of membrane chemistry on membrane structure. And now we can actually correlate with performance even without doing any tests. We can put it in the microscope, simulate it, and say, hey, this will be better because this looks like that. And whatever it did in your chemistry, this is what happened at the structural level. So we are very eager to move forward in this direction to design new types of RO membranes, and you will see later other types of membranes. And if people are interested in this, I'm very happy to talk with them and collaborate with them on this area. So now we move in a completely different direction. So we learned about what happens in porous membranes. You want all pores the same size. Non-porous membranes, free volume elements of the same size, densities to be the same. But what is ideal? What is ideal is if you have a lot of pores and all pores of the same size. And if you want to do desalination type applications or small molecule separations, they have to be angstrom scale. So can you have angstrom scale pores in a membrane of all the same size? No free volume, just holes going through, all of the same size and a lot of it. Actually, you know what? Biology does this already, and it does it really well. So again, I'm going to go back to reverse osmosis. We already learned all about this. It's solution diffusion. Water has to go into the free volumes in here, and the polymer has to move around. So you need activation energy, and then the water goes in from one free volume to another, then comes out. So really slow probabilistic process. But if you look at biological membranes, it's very thin. It's not 300, 200, 100 nanometer. It's 5 nanometers. So 20, 30, 40 times thinner. And it has straight through highways for water to go through, in this case, for example. And the channel doesn't have to move around for water to go through. So the activation energy is low. And this protein, this aquaporin, only allows water to go through. So this is an ideal channel-based mechanism that our bodies already use for doing desalination. So there's something to be learned here. So this is the journey I'm going to take you for the next 15 minutes, and we'll come back to the original idea a little bit. So let's talk about these biological water channels. I got fascinated by these because they're just so beautiful. I never knew that they could have any applications, but I think there is some potential for these in the future as well. So these proteins are tetramers. So there are 4 of the same molecules. And the pore is in the center of each one of them where the water goes through. There's some controversy about what the central pore does in here. But each pore, each monomer does water filtration, and each monomer has 6 domains that span the membrane, and then 2 loops. When you fold this up in a membrane, in C, you see that it makes this beautiful hourglass structure that allows a wire of water to go through. And the inside of the membrane, inside of the channel or the protein is hydrophobic. It doesn't like water, so water doesn't stick to it, just goes straight through. And it also has charge at the mouth, and it's only 3 angstroms in diameter, so it rejects everything, including protons. And it's very hard to make anything artificial like this. But this does water transport at the rate of 3 to 4 billion water molecules per second while rejecting everything. So it's pretty amazing what this can do. So we want to work with these kind of proteins because there are other proteins in our body that do very exciting things like this. There are ones that can only allow potassium to go through while rejecting sodium, with a discrimination of 10,000 to 1 that nobody can match in synthetic systems. So we want to work with membrane proteins, so we need to learn about these proteins. How do they work? One of the most important things to know is they are hydrophobic. They don't like water. So this is an aquaporin. The residues are colored in pink, all the hydrophobic residues, so you know you can't put them in water. They'll stick to each other. So in nature, in biology, they're found in these lipid bilayers. And these lipid bilayers are basically chains that are hydrophobic connected to a head that's hydrophilic. And this part of the protein is hydrophilic, the top part, and the middle part is hydrophobic. So it self-assembles and orients automatically. So now if you want to work with these proteins, when you purify it, you have to put detergents that coat the hydrophobic part so it's still stable. So that's what you need to do to make membranes out of membrane protein. So I'm going to give you some examples of what we did with this. The first thing we did is to not work with lipids. Lipids are unstable, they're oxidation sensitive. So we started working with blockopolymers that have a hydrophobic and a hydrophilic part, so they self-assemble just like lipids. So we started using them instead of lipids. And then we started working with different types of proteins. So I'll come back to aquaporins later, but we decided to work with some more stable proteins and target different sizes. And you can ask me questions later about where is my aquaporin membrane. We'll discuss that if you have questions. But this protein is OMP-F, outer membrane protein F. It's a trimer, so 3 of them together. It has a 1 nanometer pore, so a little bigger than what you can use for desalination, but it is bulletproof. We put them in chloroform methanol mixtures, and they still survive, which is amazing for a protein. So we want to work with this class of proteins called beta-metal proteins. The other amazing thing that you can do is you can pack them in these blockopolymers, polybutadiene polyethylene oxide blockopolymers, and make a 2D sheet that looks like a crystal. So all this black dots you see, these are proteins. And this scale bar is 100 nanometers. So we can make 5 micron sheets of these proteins and blockopolymers that have 1 trillion proteins per centimeter squared. So talk about pore density. This pore density is enormous. So of course, we wanted to make membranes out of this. It took us 10 years to make something useful out of this, but we did. And the idea was very simple. We take a support membrane, porous membrane, and it's negatively charged. So we put this positively charged polymer on it. And then we put our sheets on it, and the sheets have a carboxylate group. So it's in water, it's negatively charged. And we keep building this sandwich or cake till we don't see any of the pores of the support membrane. So we've covered everything, and then we do simple aqueous chemistry to cross-link everything. So this ends up with a pretty nice membrane for OMP-F. So we started thinking about other proteins, larger proteins. And this is a designed protein that's a little bigger. This is about 1 nanometer by 0.8. This is about 1.5 nanometer, and this is circular in 1.5 nanometer. And we made membranes using the same method, and it has some amazing performance. Actually, I'm going to skip this one, but you can download the paper if you want to read it. I'm going to show you this. So when we were working on this paper and we sent it for review, the question was, and the criticism was, that you are using crappy comparisons. So we were pretty incensed. So we've bought every membrane, nanofiltration membrane on the market that we could buy. And we tested them. We tested their molecular weight cutoff, and we tested their water permeability. So this is liters per meter squared hour per bar. So it's a unit of permeability, and this indicates what you can reject from these membranes. So this range is the nanofiltration range. So the OMPF protein was 20 times better than anything in its range. And this alpha hemolysin protein was 200 times, with this having the same sharp selectivity for rejecting 1,000 Dalton molecules. It was 200 times better than anything commercial. So enormous improvements in permeability for the same selectivity. Now, I was in industry for a while. I totally understand that stability is important, and these are protein-based membranes. So the long-term stability is still a question. They can survive up to 30, 40 PSI, but we don't know how much you can push them. And it's expensive. You use membrane proteins, and you have to do a lot of unconventional processing to make these membranes. But I think there is a space for this. And I'll give you a list of applications where this could really work very well, where you have high selectivity, high value products, and where you want precision, and you can't just make lots of membranes. You need compactness. So this can be done. This can be used. But again, being an engineer, I started thinking about how can we make this concept that we learned from biology more practical? Can we use it for, can we make channels that are not protein-based? Can we make channels that are made synthetically, right? So we started doing that, and we took the lessons we learned from proteins of making these flat sheets with very high density, trillions of channels per centimeter squared, and trying to make them flat. And we also learned that in the channel, if you prevent hydrogen bonding with the wall, you can have very fast transport of water. So we started using this, and we lucked upon this field of artificial water channels. So Mihai Barbeau from France coined this beautiful term and started this field. And what this is basically trying to copy aquaporins using artificial channels. And we started working with the leaders in this field in 2012. And we work with these unimolecular channels. It's basically one molecule that looks like a protein. And then Alex Noy's group in Lawrence Livermore has these carbon nanotubes, very narrow nanotubes that can also be called water channels. And there are self-assembled channels that are beautiful. They self-assemble once you put it in the membrane. But I'm going to talk about this today, this unimolecular channel today. So the unimolecular channel we're going to talk about are these peptide-appended pillar fibrine. I call them PAP5. So these are basically these benzene rings with 2 hydroxyls on it in a ring. So 5 of them in a ring. So it makes a 4.7 angstrom pore. So we are talking about sub-nanometer separations. And then what you do is you put chains on each end on these hydroxides. And they're usually peptide chains that are very hydrophobic. So again, it looks like the hydrophobic outside of aquaporin. And then when you put it all together, you can make, so again, this is peptide chains, about 5 angstrom pores. And then there's interchain hydrogen bonding. So it makes like a rigid tube that can go into a lipid bilayer or another polymer bilayer that we make. So we did some simulations to prove that this is actually single file water transport. And this study showed at that time, it was the only channel that approached the permeability of aquaporin. So that was a pretty interesting idea because now you can get away from proteins and use artificial channels. And then we were able to make membrane. So this is kind of like the timeline. This channel was discovered in 2013. We characterized it in 2015, and we made a membrane in 2018. And this membrane also outperforms commercial nanofiltration membranes by 3 or 4 times, not as much as our proteins. There's some ways to go here too, but it definitely does a good job. And it has the advantage of scalability. It's not as unstable. It can be put in solvents, all these other things. So the outcome of all this is that we can use these kind of nanometer pore size membranes for antibiotic separations and downstream processing of nucleotide-based therapeutics or other separations that are difficult to do with nanofiltration right now. We have a project where we are dehydrating membrane proteins, actually these crystal-like things, and making transport fabrics or high vapor transport fabrics that are really working very well and provide lots of protection against any kind of biological attack. And dairy separations, food processing, and our new project is on rare earth element recovery by designing these artificial channels to have specific ligands on them. So these are ideas that we could use. Again, so this is, again, a little at the cutting edge of what can be done right now. So what we're gonna do now is switch over to something a little more practical. And so we're gonna think about all that we learned. Can we make something that's really practical and helps with all this knowledge, right? Because all the things that I just said, they're at the cutting edge, they can do a really good job, but they need some development to make them into something that can be widely applied. But I'm going to talk about something that is something a little more practical here. So we started working with gas separations after moving to UT. There's Benny Freeman here who has a wonderful lab, a very well-known lab in the area of gas separations. We're learning a lot and trying to apply our ideas. So for gas separations, the scale is huge. So the productivity has to be good, the selectivity has to be good, and these two are somewhat solved in the field. It could do better with selectivity in some applications, I think. The stability is a challenge if you use carbon dioxide. If you're doing carbon capture, doing carbon dioxide, the membranes age very quickly. That could be a problem. And cost is a problem. So these membranes are, this is just a guess. We did some looking around, and $50 per meter squared for many natural gas refining processes. So this is a challenge that could be overcome if we think about this rationally. So we went back to what I really like, this really cheap material that's widely used. Can we use a thin film composite platform for making gas separation membranes and use the polyamide chemistry or some variant of it to make membranes? So the cons that we are dealing with when we use this kind of application, this has been thought about before, is this works for water, this chemistry, but it's susceptible to defects or pinholes that kill it for gas separations in many ways. So you really have to be thoughtful about what you can do with it. And again, I just showed you it's difficult to control the homogeneity. You saw the wide distribution unless you do some special things to make it narrow. So we had an idea. So this is what we started drawing. This is a cartoon on the left side in yellow here, where we are talking about the free volume distribution, and it's all different sizes. So it has a broad distribution. So this leads to low selectivity. What if we can put in, say, this channel? So there are many other channels out there, but this microcycle is 4.7 angstrom. If we build it into the structure of these polyamide type membranes, and this is the chemistry we use, and we have a lot of these macrocyclic structures in there, we'll overwhelm whatever the background is. And if we can tighten this up a little bit with a new void size that dominates everything, and this should improve selectivity. So we were able to make this. It took us a couple of years to do this. So this is a support membrane with holes. We make a conventional polyamide membrane with all the structures, the hoodoos I call them on there. And we are able to make it with pillar rings, and they look very different. They look more fibrous over here. And the other way they look different is the thickness. When we make our gas tight type conventional polyamide membranes, they're about 300 nanometer thick. But when we put the pillar rings in them, they become much thicker. So this is interesting because it's indicating that perhaps we are decreasing the density, so the volume goes up. So that's interesting. And then the results of the performance tests are even more interesting. So if you're looking at hydrogen permeability versus hydrogen over carbon dioxide selectivity, you see that it goes up by quite a lot, and the permeability goes up too. So these permeabilities are not that high for commercial applications, but we'll talk about that in a second. But the selectivities can go up by orders of magnitude if you select the ring that you're using right. So we really can get really high selectivities with these membranes. and they compete with all the polymers and gases. You have trade-off curves for almost every gas pair, and you can get really high performances. Our recent tests have even moved it to this side, and even this one is over the trade-off line now. So we can really make the state-of-the-art membranes, and the state-of-the-art membranes are very stable because this highly cross-linked polyamide polymer is very stable to plasticization. So what I'm showing here is if you have high carbon dioxide pressure and you make this state-of-the-art polymer and make a membrane out of it, the permeability goes down as the matrix compresses, but then it starts plasticizing the polymer and the permeability, it starts going up. We tested under the same pressures and we have a very stable performance. Note that our permeability is just low, right? So it's much lower than what's for this polymer. But for certain applications, by adding different rings, I think we can adjust that. So in the end, the questions that we are addressing is we can improve permeability by having a thin structure. So most of gas separation membranes are microns, many microns thick, and we can get to below micron thickness. We are trying to improve the nanoscale homogeneity by adding these rings in there. And we are doing both tomography and simulations to understand it better. We have very good mechanical resistance, and this is an immensely scalable technology. The cost is, again, this is a very simple calculation, but it's definitely in this range of $10 per meter square or less. And most of the cost is from the ring structure that we are making. The TFC itself is a relatively cheap material to make the polyamide TFC. So that's what I wanted to say. So we learned from nature and we are trying to go different ways with it. And we are very excited about trying to use this for different applications. So with that, I would like to end the talk and acknowledge my collaborators here. I'm sure I've left some out, but they've been very helpful. And the bottom is my research group. This is the Longhorn Santa that my neighbor puts out during Christmas. So I wanted to show that to you guys. And with that, I would like to end and open it up for questions.
Thank you so much, Manish. This has been a really interesting talk. So now let's move to our Q&A portion of the webinar. And let me start with when you were speaking about the gas separations, some of the latest work, one of the questions is, do you think that the increased thickness leads to better mechanical stability over time?
So that was one of our earlier tries where we had a few microns. Our newest tries show that we can get to less than, we can get to 400, 500 nanometer. And I think the thickness definitely benefits the stability, but the cross-linked, highly cross-linked nature of this polyamide type structure also helps with stability. So it's both, but I think we can also make it thinner and still be just as stable.
Great, thank you. Have you made any tests of these protein-based membranes in non-aqueous systems? Would they also work well, for instance, for NF or for organic solvents?
Yeah, so this is a good question. That is maybe a little harsh. I'm afraid to go there, but we will try it eventually. We have used it for gases. So this was a big surprise for us. We dehydrated using a new protocol we've developed. So think about this. These are the proteins that are in your body, and we are taking it out of water and drying it out. And we can still do vapor separations using it. So that's how much you've taken the proteins away from its natural environment. I think it may work, but I'm afraid because the polymers that we use to put these proteins in, they themselves are not that stable in many organic solvents. So my concern is more with the matrix, also with the matrix and not just with the protein. So perhaps organic solvents is a stretch, but we'll try. We've only taken it up to vapor now. So that itself was a shock for me.
Thank you. There was also a question, did you consider using self-assembled polymeric membranes as supports for TFC membranes? These self-assembled membranes are isoporous with high pore density.
Yeah, this is a great idea. We just use the cheapest membranes we can find, but that may help us in improving the performance of our membranes. But what we are trying to go for, so when people make reverse osmosis membranes, they also use their own polysulfone cast membranes that are phase inverted and cheap to make. These isoporous self-assembled membranes are somewhat expensive to make right now. But in terms of performance, I also agree with you that it might be a good idea to show how much you can push the performance on these membranes.
I think there was a follow-up question when on the gas membranes that you're working or collaborating with Benny on. Could these be formatted as hollow fiber?
Oh, wow. We are trying. As you know, making polyamide membranes that are tight, you may know, whoever asked this question, is not easy. We are trying. If you have ideas, please email me. We can talk. Teach me how to do this. But we are trying. We have some initial success, but the pinhole defects are a problem with hollow fibers. But really almost getting there, I think. So.
And there's also a question about the maximum operating temperature for the protein-based membranes.
Yeah, so the protein-based membranes, the proteins themselves are stable up to 90 degrees. The ones that we use, 90 degrees C. So I think that's our limit. But we haven't pushed it beyond. We haven't pushed the temperature at all. But the protein themselves are stable up to 90 degrees C.
And there's a question on the, is there a chance to get the large OMP with any Aquaporin?
Oh, so this is Joachim. I know Joachim, hello.
Yes.
Yeah, so I didn't show this work, but we can do what Aquaporins can do with a designed version of OMP-F. So there's a paper we published in 2018 where we take the OMP-F and we can make it any size using an algorithm and then that Costas Meranas developed, and we redesigned the pore to do the same thing that Aquaporin does, at least in terms of rejecting salt and transporting water. So this is doable. We haven't been able to make membranes with it. We don't have the time or the resources to try all these ideas, but we are going there someday, I think, soon. So.
You're also getting congratulations, great presentation messages from the audience. And a question, did you test these membranes for gas separation under humidity?
As you guys know, the Freeman lab here is a really good lab for doing these experiments. We will. We haven't done this yet.
Now, how do you think the microscopy technique, how do you know the microscopy technique you described for reverse osmosis membrane can be used for improving performance in new membranes?
Yeah, so this is a good question, and it really goes to thinking about how you can tailor membranes for your application. So if you read the paper that we wrote, there's a line in there saying that if you can decide what selectivity you want, so if you design your selectivity saying I want 10,000 to 1 salt or less for brackish water applications, you fix it there and you try to find the density that'll give you that rejection. And then you tighten up your membrane so that it is centered around that density and slightly higher than that density. So you'll get the highest permeability and you'll maintain your salt rejection. And you can also think about operationally how rejection is changing and design it for maximum energy savings. So this is doable now if you can. I mean, we need to do more work on this, but I think it's almost doable now if we do some more calculations and thinking and do a few more studies. So the future is in tailoring these membranes to your exact application.
Again, you're getting kudos on your great work. And another question, the high flux membranes. So how do they compare against thermodynamic minimum values of separation? Sure.
Yeah, so this is a good question. You can't beat thermodynamics, but I don't think our membranes are optimized. So the thermodynamic minimum has to do with selecting the ideal separation, right? we don't want to do ideal separations for many of our applications. So if you can make a membrane that does what you need to do, but do it at a higher flux or a higher permeability, then you can save energy from that. So brackish water membranes are far away from the thermodynamic minimum. I think seawater membranes may be over-designed, and there could be some play there too. So seawater, we all know, is seawater membranes, RO membranes are very close to thermodynamic minimum, so we can't do much with that. But all these other applications, there is a potential to save energy and cost by doing what we are trying to do here.
Thank you, Manish. This has been a very interesting talk, and we should start wrapping up now. So thank you again also to our live audience for all of your questions and your active participation. As we mentioned earlier, a link to the recorded event will be sent via email in the coming days. And now I will pass the microphone over to my colleague, Canavis. He will close our event. Happy Friday and have a good weekend.
Hello, everyone. My name is Canavis Smith, and I wanted to formally thank each of you for joining today's webinar, and we hope the conversation was valuable. Next, we wanted to highlight a few of our professional development short courses and future webinars. As you have heard today, lifelong learning and research is fundamental in preparing individuals to remain competitive in today's workforce. Texas Engineering will be hosting our annual forensics conference, February 11th and 12th. This conference brings together the best of academic and industry for an exciting exchange on forensics engineering. By using real-world case studies such as hurricanes, structural failures, and foundation issues, this conference focuses on lessons learned across a variety of topics. So please be sure to visit our website to learn more about registering for this virtual experience. Staying up to date with relevant skills is always needed in tackling some of the world's biggest challenges. To support the needs for working mechanical and petroleum engineers, UT Engineering has created an online mechanical graduate certificate in controls and a petroleum engineering graduate certificate in data analytics, specifically built for the oil and gas industry. Both of these graduate level certificates are created for degree seeking and non-degree seeking students to provide them tools to optimize process and systems that you use every day. Visit our website today to learn more about our simple application process. Next, we wanted to highlight upcoming courses related with our engineering skills, pipeline technology, and engineering fundamentals. If you or your organization need additional training in this area, please contact our PTEX department today. Next, we will also want to thank the 3 units of the Cockrell School of Engineering that helped put this wonderful program together. First is our research relations team. This team partners with industry to solve some of the world's biggest problems in energy, water, transportation, sustainable separations, and many more. The Office of Research Relations works to facilitate and derive high value from research collaborations between companies and UT researchers. If your company would like to partner with the university or Manish Kumar to explore additional bio-inspired research opportunities, please email the Research Relations Office to initiate a discovery discussion. Next is the Texas Engineering Executive Education, who works to reskill and upskill companies' current workforce, either through our master's degree programs, graduate certificates, or short courses. So if you have a need around STEM education and training for working professionals, make sure to contact our department to learn more. And last but not least is our PTEX department, the Petroleum Extension of Texas. This department has been around for over 75 years, serving the oil and gas professionals, either through e-learning, publications, online and in-person training. We will have the training you need for the oil and gas desires. All 3 units are here to serve you and your company through education, training, and research. So feel free to contact us at any time, and we will love to collaborate on helping you reach your company's full potential. As we continue in the Text Talk series, I wanted to make sure you're aware of our upcoming webinar. On February 12th, Dr. Michael Perch will be discussing data analytics and machine learning for energy, geoscience, and engineering. This talk will present ideas for adding value through data to the oil and gas industry. We hope each of you will join us for a future webinar, so mark your calendars today. If you would like to provide feedback on today's webinar, or to learn more about receiving CEUs for today's talk, make sure to complete the evaluation survey in your email following this presentation. Once again, we would like to thank you for joining us today. We hope you have a great weekend and hook 'em horns.